Welcome to today's paper reading. Today's paper is titled, Demystifying LLM-based Software Engineering Agents. This paper was published on the AR14 preprint by Chunqiu, Stephen Xia and colleagues from the University of Illinois Urbana-Champaign. Recent advancements in large language models, LLMs, have significantly advanced the automation of software development tasks, including code synthesis, program repair, and test generation. To address the complexity of current autonomous LLM agents, we introduce Agentless, a simpler approach that employs a two-phase process of localization followed by repair, without relying on complex tools or future action planning by the LLM. Our results on the SWE-bench Lite benchmark demonstrate that Agentless achieves the highest performance at 27.33% and the lowest cost of 34 cents, outperforming all existing open-source software agents. To ensure a more rigorous evaluation, we created SWE-bench Lite S by excluding problematic issues. This work underscores the potential of simple, interpretable techniques in autonomous software development and aims to reset the baseline for future research. Large language models, LLMs, have become the standard choice for code generation tasks. Models like GPT-4 and Claude 3.5 have shown significant capabilities in synthesizing code snippets. However, their application to repository-level software engineering tasks remains understudied. The SWE-bench benchmark was developed to address this gap, focusing on real-world software engineering problems involving GitHub issues and Python repositories. A subset, SWE-bench Lite, specifically targets bug-fixing issues. Agent-based approaches, which equip LLMs with tools and allow for iterative actions, have been proposed to tackle these challenges. However, these approaches face limitations such as complex tool usage, lack of control in decision planning, and limited self-reflection capabilities. This paper introduces Agentless, an agentless approach designed to address these limitations and simplify the process of solving software development problems. Figure 1 provides an overview of the agentless approach, which consists of two main phases, localization and repair. In the localization phase, Agentless first converts the project codebase into a tree-like structure format to identify the top and most suspicious files that need editing. It then narrows down to specific classes, functions, and variables within these files. The repair phase involves generating multiple candidate patches, filtering out those with syntax errors or test failures, and selecting the top-ranked patch for submission. This approach leverages LLMs without allowing them to autonomously decide future actions or operate with complex tools. The agentless approach is divided into two main phases, localization and repair. In the localization phase, the process begins by converting the project codebase into a tree-like structure to identify the top and most suspicious files that need editing. Next, it narrows down to specific classes and functions within these files, and finally, it localizes to precise edit locations within the code. The repair phase involves generating multiple patches to solve the issue, filtering out those with syntax errors or test failures, and selecting the final patch through majority voting. Figure 2 illustrates the skeleton format used in the localization phase of Agentless. This format includes only the headers of classes and functions within the file, along with any class fields and methods, represented by their signatures. Additionally, comments at the class and module level are kept to provide further context. This concise representation is particularly useful when dealing with files containing thousands of lines, as it allows for more efficient processing by the LLM. Figure 3 illustrates the search/replace-edit format used by Agentless to generate patches for code repair. This format consists of two main parts, the search code snippet, which is the original code to be replaced, and the replace code snippet, which is the new code to replace the original. This method focuses on creating small, efficient edits rather than generating entire code snippets, making the process more cost-effective and less prone to errors. The experimental setup involves the use of the SWE-bench dataset, specifically focusing on the SWE-bench Lite subset, which contains 300 problems with tests for functional correctness evaluation. The agentless system is implemented using GPT-4o with greedy decoding and a sampling temperature of 0.8. This setup results in 421 patches generated per bug. For comparison, Agentless is benchmarked against 13 agent-based approaches, including state-of-the-art tools and a retrieval-augmented generation (RAG) Agentless baseline. In evaluating Agentless on SWE Bench Lite, we observe that it solves 82 out of 300 problems, achieving a 27.33% resolution rate. This performance is competitive with prior agent-based approaches, despite using a much simpler design and lower average cost of 34 cents. Agentless also stands out by fixing 15 unique issues that no other open-source agent can resolve, and it offers more unique fixes than even the top commercial solution, Alibaba Lingming Agent. This indicates that Agentless can complement existing commercial setups. Additionally, Agentless performs well in localization, with a simple hierarchical approach that remains competitive with previous agent-based methods. This approach helps in minimizing cost while effectively localizing issues. Table 1 presents the performance results of Agentless and various agent-based approaches on the SWE Bench Lite dataset. Agentless successfully resolves 82 out of 300 problems, achieving a 27.33% resolution rate. The tool demonstrates competitive performance with an average cost of 34 cents, significantly lower than many agent-based methods. Additionally, Agentless shows a 34.3% accuracy in identifying the correct file-level location for patches, indicating its effectiveness in localization tasks. Figure 4 presents a Venn diagram illustrating the unique issues resolved by Agentless compared to top-performing closed-source/commercial and open-source approaches. Notably, Agentless addresses 15 issues not resolved by any existing open-source agent, demonstrating the effectiveness of an agentless approach. Additionally, Agentless provides more unique fixes than the top commercial solution, Alibaba Lingming Agent, indicating its potential as a complementary tool to existing commercial agent-based setups. Table 2 presents the performance of Agentless across its 3 localization steps. Initially, Agentless accurately localizes to the file level in 77.7% of cases, involving 3,305 lines of code, lock. In the second step, it narrows down to related classes and functions, significantly reducing the context to 813 lock. The final step focuses on exact edit locations, further reducing the context to 246 lock without substantial loss in localization accuracy. The average cost per step ranges from 2 cents to 5 cents, demonstrating Agentless's efficiency in both localization and cost management. Table 3 presents the performance of various repair setups for Agentless. Initially, generating a single sample achieves 70 correct fixes at 11 cents per bug, outperforming most prior open-source approaches. Enhancing to multiple samples with majority voting improves performance to 78 fixes. The full Agentless setup, including test filtering, reaches 82 fixes, demonstrating a 41% potential for repair issues. In this section, we delve deeper into the problems within SWE Bench Lite. We classify these problems to gain a clearer understanding of what types of issues Agentless and previous methods can address. Specifically, we manually classify each problem based on its description and the ground truth developer patch. We examine 3 main dimensions: description quality, solution presence in the description, and location information. For description quality, we find that 90.7% of the tasks contain sufficient information, but 9.3% lack enough details. Regarding solutions, 73.7% of issues do not provide any solution steps, while 4.3% include misleading solutions. For location information, less than 10% of issues provide exact line locations, but this increases to around 50% when considering file-level locations. These classifications reveal potential issues with the benchmark, such as unsolvable questions and misleading solutions, which have not been adequately addressed. Figure 5 categorizes the problems in SWE Bench Lite based on description quality, solution presence in description, and location information. It highlights that 9.3% of problems lack sufficient information, 4.3% provide exact patches, and 10% offer complete solution steps. Additionally, it notes that less than 10% of issues specify exact lines to fix, while about 50% provide file-level location information. Table 4 presents the performance and ranking of various tools on the SWE-bench LiteS benchmark. The Alibaba Lingming agent leads with 87% of problems resolved, followed closely by other tools like Factory Code Droid and Autocode Rover v2. Notably, GPT-4o Plus Agentless achieves 82% resolution, placing it in the top tier. In contrast, the 20th ranked tool resolves 0% of the problems, highlighting significant disparities in performance across the evaluated tools. Figure 6 illustrates the solve rates of various open source and closed source approaches across different problem categories in the SWE-bench LiteS benchmark. The red dotted line represents the average solve rate for each approach across the entire benchmark, highlighting the performance differences between open source, orange, and closed source, indigo, tools. The solve rates are categorized by problem types, showing how each approach performs under different conditions. In the realm of using large language models, LLMs, for coding, LLMs have shown remarkable capabilities in tasks such as code generation and understanding. These models have been applied to various software engineering tasks including program synthesis, code translation, program repair, and test generation. Additionally, code-specific LLMs like Codex and CodeLlama have been developed by training on large datasets of code snippets. To evaluate the performance of LLMs on coding tasks, benchmarks like HumanEval and MBPP have been widely used. These benchmarks include test cases to verify the correctness of LLM outputs. More robust and multi-language benchmarks have also been proposed, as well as benchmarks focusing on real-world software engineering issues. Recently, agent-based frameworks have gained attention for solving software engineering tasks. Examples include Devin and SWE Agent, which use LLM agents to interact with repository environments. However, Agentless offers a simpler, cost-effective solution without the need for complex agent setups. In this study, the authors propose Agentless, an agentless approach designed to automatically address software development issues. Agentless employs a straightforward two-phase process involving localization followed by repair. Unlike previous agent-based methods, Agentless specifically restricts the large language model, LLM, from autonomous tool usage or planning. The evaluation conducted on the widely used SWE-bench Lite benchmark indicates that Agentless not only achieves the highest performance among other open-source techniques but also significantly reduces costs. Additionally, the authors have performed a detailed classification of problems within SWE-bench Lite, aiming to provide new insights and construct a more rigorous version of the benchmark, SWE-bench LiteS, by eliminating problematic issues. Thank you for watching.